Okay, so ladies and gentlemen, you are all welcome to my YouTube channel. If this is the first time you are coming to this of my channel, please subscribe. Today we are going to look at acid-base balance. Acid-base balance. So generally in the body, our body fluid is generally surrounded with a lot of hydrogen ion concentration. So for example, now when we have a substance like this, so when a substance actually accepts or donates, when a substance donates hydrogen ion, when you have substance that donates hydrogen ion, that donate hydrogen ion, that substance is considered as an acid. Then when you have substances that accept hydrogen ion, then that substance is considered as a base. And of course, this acid is divided into two. We have a strong acid, and then we also have a weak acid. Also, in the case of base, we have a strong base, and we have weak base. So when you say strong acid, it means that they are acid that can completely ionize in water, while weak acid are those acids that are partially ionized in water, while strong base is also a base that strongly ionized in water, while weak base is also partially ionized in water. So generally, our body fluids is made up of a different concentration of this hydrogen ion. Like for example, the blood, we have the concentration of hydrogen ion, in the blood is around 40 nano equivalent per liter. 40 nano equivalent per liter. But nano is actually a huge zero here. There is a huge zero here. So because sometimes the concentration of hydrogen ion to be expressed is very, very low, that is why it's usually expressed in the form of pH. What is a pH? A pH is a negative logarithm of hydrogen ion concentration. And of course, what is the relationship between pH and hydrogen ion concentration? So what actually happened generally when we say pH is equal to, actually it's usually expressed as log distant 1 all over hydrogen ion concentration. It means that you can clearly see that from here you can see that the pH is an inverse of hydrogen ion concentration. It's an inverse. So what will happen? It means that since they are inverse, it means that whenever the hydrogen ion concentration increases, it means that the pH will decrease. So when hydrogen ion concentration increases, then the pH will decrease. So it's an inverse. So if one increases, then the other one will decrease. And at the same time, if hydrogen ion concentration decreases, then of course the pH will increase. So that is how it's happened. So they are directly sorry, they are inversely related. So if one increases, then the other one will decrease. So pH decreases when hydrogen ion concentration, pH increases when hydrogen ion concentration decreases. So they are inversely related. And then the next thing is, but here we are saying that the pH is a logarithm of inverse of hydrogen ion concentration. So because it's an inverse, that is why we can even change it to this negative. So this negative, it means that it is actually an inverse. So that is why we usually express pH as pH is equal to minus log of hydrogen ion concentration. So that is pH. So pH is a negative logarithm of hydrogen ion concentration. So, but in the case of the blood, that we see that the concentration of hydrogen ion is 40 nano equivalent. So it is actually not easy to express it in that form. So that is why we express the pH, we express hydrogen ion concentration in most cases in form of pH. Okay, so now the next thing that we are going to look at, pH is a unit of measure which describes the degree of acidity or alkalinity. That is the basic of a solution. So generally, you can use a pH to know whether a solution is acidic, basic, or neutral. In fact, within the pH, it will give you an idea whether the solution is a strong acid, strong base, weak, or neutral. So usually the pH has a scale which ranges between 0 to 14. So low pH value correspond to high concentration of hydrogen, as we said previously. It means that whenever you have low pH values, that tells you that you have high concentration of hydrogen ion, and high pH values correspond to low concentration of hydrogen ion. So that is to tell us that the higher the pH, then the lower the concentration of the hydrogen ion. And the lower the pH, the higher the concentration of hydrogen ion. So that is the inverse relationship. So now, pH value, the pH value of a substance is directly related to the ratio of the hydrogen ion and hydroxyl ion concentration. So if hydrogen ion concentration is higher than OH, then the material is acidic. You see, generally, you can have a substance or a material that has both hydrogen ion concentration and OH. But to give you the nature and the idea of what kind of substance is that, then you now try to check between the hydrogen ion concentration and the OH, which one is having higher concentration. So if hydrogen concentration is higher than the hydroxyl ion, it means that the material is acidic. But inversely, if the OH, that is hydroxyl ion concentration, is higher than hydrogen ion, then the material is basic. And 7, when you have a pH of 7, is neutral. And when the pH is less than 7, it is acidic. And when it is greater than 7, it's basic. So you should get that, ladies and gentlemen. So the pH is, you can use pH to tell you whether the substance is acidic, basic, or neutral. So in this case, pH of 7 is neutral, pH of less than 7 is acidic, and then pH of greater than 7 is basic or alkali. Then we have pH scale. So the pH scale corresponds to the concentration of hydrogen ion. So for example, pure water, that is hydrogen ion concentration is 1 times 10 raised to the power of minus 7. So therefore the pH will then be 7. So that is why pure water is normally neutral, and sometimes it's very, very important to, if you are actually taking a water flow from particular environment, to try to check their pH to see if they are acidic, basic, or neutral. But I can tell you that most of the water that we are taking, especially in Nigeria, because they are not pure, and in some cases you see that they are acidic. In some cases we are taking acidic water. So this is actually the pH scale, though the pH values are shown by different color in universal indicator. So you see strong acids, like for example, a pH of 1, 2 to 3 is strong acidic. And then 4, 5, 6, 7, 4, 5 to 6 is weak. And then of course a pH of 7 is neutral, and then 7, 8, 10, 11 weak, and then from 12, 13, 14 strong alkali. So this is a pH. And then the next thing is an acid. What is an acid? What is an acid? So any compound which forms hydrogen ion in a solution, that is a proton donors, they are called an acid. So an acid is any substances that donate a protons or releases a protons. So whenever you have a substance and when adding it in a solution, it releases or it donates hydrogen ion, that substance is considered as an acid. Then a base. A base is any compound that combines with hydrogen ion in a solution, or proton acceptors, or they generally accept protons. So that substance is considered as a base. Like examples of an acid, we have carbonic acid. We have carbonic acids. And then example of a base, we have bicarbonate. So carbonic acid releases hydrogen ion, and then bicarbonate accepts hydrogen ion. So the normal, like for example, a blood, the normal pH for blood, or the fixed pH of blood, is 7.4, but it has a range of between 7.35 to 7.45. That is the normal pH of the blood. So you can have actually a conditions like physiological state resulting from abnormally low plasma. It's called metabolic acidosis. And that is to tell you when the pH is below 7.35. It means that the pH is lower than expected. So that is to tell us that when the pH is below that, then there is metabolic acidosis. And we have alkalosis, which is a physiological state resulting from abnormally high plasma. So when there is a low plasma, it's acidosis. And when there is a high plasma, is alkalosis. So when a pH is below 7.35 of the blood, the condition is called acidemia. And when the pH is greater than 7.45, then the condition is considered as alkalemia. So what are the measurement of pH? How do we measure a pH? So we measure pH by using pH strips, pH meters, and pH indicators. This is how we measure the pH of a material. We use pH strips, pH indicators, and pH meters. These are the instruments that are used in measuring pH. Then we have some important indicators used in a clinical biochemistry laboratory, which are listed here. So when you said pH, when you said indicators are generally materials that are used to detect whether the substance is an acid or a base. So example of these indicators and the pH range are depicted here in the picture. We have phenolphthalein, methyl orange, bromophenol blue, methyl range, phenol rates, and litmus. So these are the examples of the indicators and their pH as well as their colors in both acidic and basic. Now, for example, assuming now you are given a solution, so you can just decide to take maybe phenolphthalein and take it. So when you take phenolphthalein and you add it inside a solution and you realize that it is colorless, so that is to tell you it's an acid. But if it gives you pink color, it means that it is a basic. So that is how it applies. So an indicator is a material that you can use to tell you whether the substance is acidic or basic. Like for example, litmus paper. When you take blue litmus paper and you put it inside a solution, so if it is acid, it will give you red. But if it is a red litmus paper and you add it inside a solution, it gives you blue color. So that is to tell you that the substance is a base. So that is an indicator. Then a pH meter. The pH meter is a laboratory equipment which used to measure acidity or alkalinity of a solution. So the pH meter measures the concentration of hydrogen ion using an ion-sensitive electrode. It is the most reliable and convenient method of measuring pH. So now the next thing is BOPAS. The BOPA is a solution that usually resists a change in pH when a small amount of acid or base is added. So generally, we have substances, and the substances that they have their normal pH, like blood. The normal pH of blood is 7.4. So sometimes an acidic material or a basic material can be added into the blood. So what will happen? If the pH of the blood is changed, either decreasing or increasing due to addition of some materials or substances, is a problem. So that is why we need this buffer system, so that to resist any changes in physiological system of the body. So typically a mixture of weak acid and a salt of its conjugate base, or weak base and a salt of its conjugate acid. So that is a buffer. So a buffer, typically if you want to define a buffer, the simple way to define buffer is that you can define buffer as a weak acid and it is conjugate base, or a weak base plus O and it is conjugate acid. So a buffer is a solution that resists, a buffer solution is a solution that resists changes in pH when a small amount of an acid is added, or a base. But a buffer itself is a solution of weak acids and it is conjugate base, or a solution of weak base and it is conjugate acids. That is described as a buffer. Now, for example, assuming now you have, let's say you have an acid, or you have a buffer system. So you have or maybe you just have an increase in hydrogen ion concentration. So when you have an increase in hydrogen ion concentration, then what will happen? The equation must reach actually an equilibrium position, because whenever we say that we have a solution at a particular pH, it means that it reached its equilibrium state. So by assuming now you increase hydrogen ion concentration, what will happen? It means that you are distorting the equilibrium system. So therefore, assuming now, for example, let's say you increase the hydrogen ion concentration, it means that the reactions that is in the equilibrium in the buffer system will shift to the right. But if you are decreasing the hydrogen ion concentration in a system, then the reactions or the equations will be actually shift to the left so that to maintain the equilibrium system and maintain the normal pH of the environment. So we have types of vapors. We have acidic vapors. So a solution of mixtures of weak acid and a salt of it is weak acid with a strong base, and that is acidic vapor. So acidic vapor is a vapor of a weak acid and a conjugate base, or it is salts. Then a basic vapor is a solution of weak base and a salt of the weak base or with a strong acid. That is a basic vapor. So these are the two types of vapors that we have. And then how vapors work. So equilibrium between acid and a base. Generally, there is equilibrium between acid and a base. Example, this is an acetate vapor. We have ethanoic acid or acetic acid which actually dissociate for the acetate ion plus hydrogen ion. So if more hydrogen ion is added to this solution, so it means that you are increasing the hydrogen ion concentration. So it simply shifts equilibrium to the left so that the hydrogen ion will be absorbed, so that the hydrogen concentrations will remain unchanged. But if hydrogen ion is removed, that is, you are decreasing the hydrogen ion concentration, maybe by adding OH, then the equilibrium will shift to the right, releasing the hydrogen ion concentration, keep the pH constant. So that is what we need to understand. So whenever there is actually an increase or decrease in pH, decrease or increase in hydrogen ion concentration, then the equilibrium will shift to an appropriate position so that the hydrogen ion concentration will be balanced and then the pH of the solution will remain constant. And that is how vapor system work. And then we have Henderson-Hasselbalch equation. Solar Joseph Henderson wrote an equation in 1908 describing the use of carbonic acid as a vapor system, and later Albert Hasselbalch later re-expressed that formula in logarithmic terms, resulting in Henderson-Hasselbalch equation. That is how we actually came up with an idea of Henderson-Hasselbalch equation. And this is how it started when you have an acid and hydrolyzes to produce hydrogen ion plus the ionates and ions. Then we are going to express it with an association, with a dissociation constant. So therefore, to do that, remember the constant, or like equilibrium constant, is to measure the concentration of the product by the concentration of the reactant. So that is why we have hydrogen ion concentration, and we have our anions as A, then we have our hydrogen ion concentration. Then at the end, logarithm or log is added to both of the equation, and that is how we arrive at PKE is equal to pH minus log of A concentration, an ion concentration divided by the acids, and at the end we have the pH is equal to pKa plus logarithm of the anion concentration divided by the concentration of the acids. So this equation in rate is described as Henderson-Hasselbalch equation. You can say pH is equal to pKa plus log of proton acceptor, which is a base, divided by the proton donor divided by the acid. So in a simple way, we can just say pKa plus logarithm of concentration of a base divided by the concentration of an acid. And that is it. That is Henderson-Hasselbalch equation. So then what are the vapor system? The buffering system in body fluid. So the buffering system in body fluid occur in both extracellular and intracellular. So in the intracellular fluids, we have phosphate buffer system, we have protein buffer system. And then the protein buffer system include hemoglobin buffer system, amino acid buffers, and we have plasma protein buffers. So these are the examples of the buffering system. So this intracellular buffering system is taking place in the cytoplasm of a cell, while the extracellular fluids include both the protein buffer system and carbonic acid bicarbonate buffer system. So this is the buffering system in a living system or in a body fluids. But specifically, actually, in this of our video, we are focusing more on phosphate buffer system. So generally, there are a lot of metabolic processes that are taking place in our body, and these metabolic processes that are occurring in our body lead to the secretion of both volatile acid and a fixed acids. And this volatile acid and the fixed acids are produced constantly in the body, are generated all the time in the body. And of course, we need to make sure that all the buffer system is maintained within the required pH. So example of the volatile acid produced is usually through oxidative metabolism of carbohydrates, fats, proteins, and averagely about 15,000 to 20,000 millimole of carbon dioxide per day are secreted or are produced through the oxidative metabolism of both all the carbohydrate, fats, proteins. And then, of course, this volatile acid is usually excreted through the lungs as carbon dioxide gas. Then we have a fixed acids. A fixed acids are those acids that do not leave solution. So once reduced, they remain in body fluid until eliminated by the kidneys. That is why sometimes if you have problem or if you see that you have some fixed acid in the blood which are not actually eliminated, it means that there is a problem with the kidney. So example of this fixed acid, we have sulfuric acid, phosphoric acid, organic acids. So, and the above are the most important fixed acids in the body. And of course, we have what you call, so most of these organic acid are generated during the catabolism of proteins, or let me just say amino acid, phospholipid, and nucleic acids, like uric acid. They are usually generated, like for example, the end product of nucleic acid in the body is uric acid. So generally, these fixed acids are generated through amino acid metabolism, phospholipid metabolism, and nucleic acid metabolism. So as they are released, they are increasing the hydrogen ion concentration of the body fluids. And as a result of that, if they are not eliminated, then the pH of the body will be compromised. So that is why we have a buffer system. So response to acid-base balance. So to balance an acid-base challenges, we need a buffering system or compensation. So buffers, the first line of defense. Buffers are the first lines of defense. And they are usually greater than 500 to 100 milliequivalent per day. So two most common chemical buffer system, we have bicarbonate system and we have non-bicarbonate system. In this non-bicarbonate system, we have hemoglobin buffering system, we have protein buffering system, and then we have phosphate buffering system. So the first line of action that trying to maintain acid-base challenges is a buffering system. And there are two most common chemical buffering systems, which include bicarbonate and then non-bicarbonate methods. So blood buffer system act instantly, regulates pH by binding or releasing hydrogen ion. So as I said, specifically, we are focusing on phosphate buffer here. So in phosphate buffer system, assuming now you have an acidic substances in the urine, then what happens? The phosphate buffer system, which is HPO42 minus or H2PO4 minus, plays a role in plasma and erythrocytes as well as the urine. So you see here, if we have H2PO4 minus plus water, then we have hydroxonium ion plus HPO42 minus. So any acid reacts with monohydrogen phosphate to form dihydrogen phosphate. So it means that if you have any acid in the urine, it usually reacts with monohydrogen phosphate. The monohydrogen phosphate is HPO42 minus, which actually form dihydrogen phosphates. So like for example, the normal pH of urine is 4.5. As the normal pH of urine is 4.5. So if you have a phosphate buffer binding to those fixed acids in the urine, what will happen? It means that the pH of the urine will be increasing. It will be increasing because you are increasing hydrogen ion concentration that are released by those acidic substances through binding the monohydrogen phosphates. So as a result of that, the pH will be increasing. The pH will be increasing due to binding of those fixed acidic substances from the urine. Therefore, what is actually happening, the monohydrogen phosphate is binding with the free hydrogen released by the acidic substances found in the urine. So, therefore, as a result of that, the pH will be actually increasing when the phosphate buffer is binding to the free hydrogen released by those acidic substances. So, and therefore the dihydrogen phosphate plus water, that is plus the acids. So the base is neutralized by the hydrogen phosphate. So therefore you can now use a base to neutralize the diphosphate buffer produced. And that is what you call titratable acidity. So a phosphate buffer is a buffer system that usually involve in trying to maintain the normal pH of the body fluids. So now the next thing is renal acids control mechanisms. So the kidneys are the third line of defense against a wide range in body fluids, which include the movement of bicarbonate, retentions like excretion of acid, and generating additional buffers. So generally, a kidney undergo a long-term regulator of acid-base balance. It can take hours to days for the correction. So now titratable acidity. Titratable acidity occurs when secreted hydrogen ion encounter and titrate with phosphate in tubular fluids. And this refers to the amount of strong base needed to titrate urine back to pH of 7.4. So you see what we are seeing here is, remember the pH of urine is 4.5. And then the pH of blood is 7.4. So in the urine, when you have a fixed acid, those fixed acid generally releases hydrogen ion. So as they are releasing the hydrogen ion, if warfarin system is not used, it means that the concentration, so the pH of the urine will go down. That is, to go below 4.5. So that is why you need a warfarin system that will be binding with the free hydrogen ion that will be released by the acids. And as a result of that, when the phosphate is binding to that free hydrogen, then the pH of the blood will be maintained within the required limits, that is using 4.5. And then now, you also need to titrate the urine so that it will go back to the normal pH of 7.4, which is equivalent to that of the blood. So ladies and gentlemen, I'm now going to show you how to carry out titratable acidity in the next video with the methods. Thank you.